afternoon everyone. Today topic name is ideal transformer and equivalent circuit of transformer and practical transformer under load condition under no load condition. Today we'll discuss these topics this class. So first what is meant by ideal transformer? Ideal transformer is an imaginary transformer which does not have any type of losses. That means no core losses, no copper losses in the transformer. And in case of the ideal transformer, the efficiency of this transformer is considered as 100% because we are not considering any losses in this transformer. Whatever the input will be there, then that will be equal to the output. According to the efficiency definition, the output by input. So, in case of the ideal transformer, the losses does not present. That's why the output will be is equal to input. That's why we are considering here efficiency of the transformer is 100%. Okay. Next, practical transformer. As we said that in an ideal transformer there are no losses in the transformer. That is, the ideal transformer is also called loss-free core transformer. But in practical transformer, there are hysteresis and eddy current losses and copper losses is present in the transformer. So that type of transformer we are calling as a practical transformer. So as we can say now, so this is, we know this, we are giving the supply to the primary winding or other secondary winding. So, and I am connecting the load to the secondary winding in this case or also primary winding. So, if you are giving a supply here, then flux will be set up in the primary winding. So, due to this flux will flow in the core is a clockwise direction. Then this flux will be linked with the secondary winding. Then induced EMF will be produced E2. Due to this induced EMF, secondary flux will be produced. The secondary flux will be linked with the primary winding. And then we are getting induced EMF is E1. Sorry. Induced EMF is E1. So, this is the process will be going on according to the mutual induction or according to the transformer principle. So, that's why the practical transformer under no load condition will be there under load condition. That we'll discuss. Next, transformer under no load condition, MCM. So, transformer under no load condition means the secondary winding of the transformer should be open circuited. Means we are not connecting any type of load to the secondary winding. So means the current I2 is equal to 0. Then we are giving the supply to the primary winding. Okay. So then primary winding supply produces the no load current I0. That no load current I0 is set up the flux in the primary winding. That flux will be linked with the secondary winding. Then we are getting the induced EMF E2 due to E2. Okay. Now, can see here under no load condition transformer, this current, no load current I0 is consisting of here the secondary current I2 is equal to 0 means this will not adding to the primary current I0. So, the primary current I0, the primary winding current, the total primary winding current I1 is equal to I0 only. That I2 dash will be is equal to 0 because this is under no load condition. I2 is equal to 0. So, then we are getting only I0, that is no load current. So, this no load current having the two components, that is working component as well as the no load component. So working component as well as the magnetizing component. that we'll discuss. See here, once IW, that is working component and magnetizing component, are known, we can determine the exciting circuit parameters. Means under no load circuit parameters we need to determine. That no load circuit parameters we are calling as a R0 and as the X0. Okay. So now you can see here the phasor diagram. Under no load condition, the V1 is lags the flux by 90 degrees. Okay. And this I0 current is the combination of two components, that is working component and as well as the magnetizing component. So then I0 is equal to vector sum of, I am writing here, I0 bar is equal to vector sum of working component plus magnetizing component current. The working component current is always in phase with the flux. Is always in phase with the flux. And working component current is always in phase with the voltage, supply voltage V1. And the magnetizing current is always, in phase with the flux. Okay. So that's why you can observe here. The working component is always in phase with the supply voltage and the magnetizing current is always in phase with the flux. The combination of these two is only the current I0, that is no load current I0. So then the induced EMF and E1 and E2 under no load condition both are in phase and opposite with the supply voltage according to the Lenz's law. This induced EMF voltage is opposite the supply voltage V that we draw. So this is the phasor diagram of under no load condition. From this phasor diagram, we are getting two components, that is working component IW is equal to I0 into cos pi naught and magnetizing component IM is equal to I0 into sin pi naught. So then the no load current I0 is equal to what I said here, IW plus IM bar, that is working component plus magnetizing component, that is vector sum. Then if you are writing the no load current I0 is equal to under root of IW square plus IM square. So then from this phasor diagram, power factor cos pi naught is equal to IW by I0 and the no load power input P naught is equal to V1 into I0 into cos pi naught. So from these equations we are finding the circuit parameter, that is no load circuit parameters, that what R0 and X0, that is R0 is equal to V0 by IW, X0 is equal to V0 by IM. So you are getting here this supply voltage is V1, is under no load current I0 is flowing here, dividing into two components, that is working component and magnetizing component. Working component current is going through the R0, magnetizing component is going to the X0. This is the equivalent circuit of the transformer under no load condition. So the next, equivalent circuit of the transformer for ideal. So they are getting what here? R1, JX1 and I2 dash. So before going to discuss this equivalent circuit of the transformer, we'll discuss about transformer under, that is load and no load condition. Then we'll discuss about transformer on load condition. So the transformer under load condition, the secondary of the transformer is connected to the load. The secondary of the transformer is connected to the load. That the load nature should be either resistive or either inductive or either capacitive or also combination. So then the current I2 flows through the secondary winding of the transformer. That is, the magnitude of the secondary current will depends on the terminal voltage V2 and as well as the nature of the load. So, the phase angle between the secondary current and the voltage depends on the nature of the load. That nature of the load is consisting of either resistive or either inductive or either capacitive. So, the operation of the transformer under load condition we'll discuss now. So, you can observe here. When the secondary of the transformer is kept open, it draws the no load current from the main supply, that is I0. Is it clear? So, this we discussed already in the under no load condition. So, the no load current induces the magnetomotive force, that is N0 into I0, because I0 is the no load current, and this force will set up the flux in the core of the transformer. In this core of the transformer, that flux will be set up due to of the no load current induces the magnetomotive force, that is N0 into I0. So, due to this N0 into I0, the flux will be set up in the coil. Okay. So, now, when the load is connected to the secondary of the transformer, then I2 current will be flows. You can observe here. This I2 current will be flows through the secondary winding. I2 current will be flows through this secondary winding. So, the secondary current will be induces the magnetomotive force, that is N2 into I2 on the secondary winding of the transformer. Means this force will be set up the flux, that is phi 2. This force will be set up the flux phi 2 in the transformer core. So, this flux phi 2 is opposes the main flux pi. According to the Lenz's law. Okay. So, then as the flux pi 2 opposes this flux pi, then the resultant flux of the transformer will be decreases. Means main flux will be decreases. And flux will be reduces and the induced EMF even will be reduces. So, the strength of the V1 is more because this phi 2 will be opposes the main flux pi. So, then flux will be reduces here. Then the induced EMF even will be reduces. Then the strength of the V1 is more compared to the E1. Okay. And an additional primary current I1 dash is drawn from this main supply. Means whatever the current I2 flows in the secondary winding, that current will be also adding to the primary winding. That current I am calling as a what? I1 dash. Okay. So, means what is the function of this additional current now here? This I2 current will be set up the magnetomotive force N2 into I2. This due to this magnetomotive force, we are getting the flux pi 2. So, this flux pi 2 is opposes the main flux. Then the main flux will be reduces. Then automatically induced EMF will be reduces. Okay. So, then the V1 will be more. Okay. So, then this secondary current is also flows to the primary winding. That current I am calling as a what? I1 dash. Okay. So, that I1 dash I am calling as the additional current here. That additional current is used for restoring the original value of the flux in the core of the transformer. So, that V1 will be is equal to E1 will get. So, means the primary current I1 dash is in phase opposition with the secondary current I2. That's why this is called as a primary counter current or primary counterbalancing current, we will say. Okay. So, and this additional current I1 dash induces the magnetomotive force in the primary winding, that is N1 into I1 dash. And this force will be set up the flux, that is called as a pi 1 dash. And the direction of the flux is same as the main flux pi. And it will cancels the secondary flux pi 2. which means it induces that because of the what? MMF of N2 and I2. Now, N1 into I1 dash will be is equal to N2 into I2. Therefore, I1 dash is equal to N2 by N1 into I2, or will be N2 by N1 is nothing but as a what? Transformation ratio. The transformation ratio is equal to what? N2 by N1 is equal to V2 by V1 is equal to I1 by I2 is equal to K. So then I am taking here N2 by N1 is equal to K. That's why I1 dash is equal to K into I2. Okay. And the phase difference between the V1 and I1 gives the power factor angle pi 1 of the primary side of the transformer. So, the power factor of the secondary side of the transformer will depends on the nature of the load. But the primary power factor will depends on only V1 and I1. That's why the phase difference between the V1 and I1 will gives the power factor angle pi 1 of the primary side of the transformer. And the power factor of the secondary side transformer we can't decide. That decide will what? The load of the transformer only, because we are connecting the load to the secondary winding of the transformer. That load should be as a resistive or inductive or capacitive. So, if the load is inductive, as shown the above, if the load is inductive, the phasor diagram will represent the power factor will be lagging, and if the load is capacitive, the power factor will be leading. If the load is resistive, that is in phase, means the total primary current I1 is the vector sum of the current I0 and as well as the I1 dash. This I0 contains how many components again? 2 components. That is what? I0 bar is equal to IM bar plus IW bar. Okay. So, the primary current under load condition is what? I1 is equal to I0 plus I1 dash. But under no load condition, I1 primary current I1 is equal to only what? I0 only. So that is the difference is for under load condition and under no load condition operation of the transformer. So then we'll discuss the phasor diagram. So that is phasor diagram of transformer and inductive load. We'll discuss this thing and the remaining things will be similar only. So before drawing the phasor diagram, some steps will be there. That step we'll discuss. First you can take the flux as a reference. I am taking here, you can observe the phasor diagram first. The flux I am taking as a reference, and induced EMF E1 and E2 lags the flux by how many degrees? 90 degrees, because the nature of the load is what? Inductive. Nature of the load is what? Inductive. That's why the induced EMF E1 and E2, the lags the flux by how many degrees? 90 degrees. You can observe here, this lags by 90 degrees. E1 is equal to E2. And the component of the applied voltage to the transformer primary winding is equal to and as well as the opposite to the induced EMF in the primary winding. E1 is represented by what? V1 dash. Okay, that is according to the Lenz's law. So that is V1 dash is opposite to the this E1. So this first one is reference. Second one, induced EMF E1 and E2 lags the flux by 90 degrees, and V1 dash is opposes the induced EMF E1 in the primary winding. And current I0 is lags the voltage V1 dash by how many degrees? 90 degrees. You can observe here. This is V1 dash by 90 degrees. Okay. And the power factor of the load is lagging because that is inductive nature. Therefore, current I2 in the secondary winding is drawn lagging E2 by an angle of pi 2. E2 by an angle of what? Pi 2. Okay. So then next, according to this steps only we are representing here phasor diagram. And the resistance and leakage reactance of the winding result in a voltage drop, and hence the secondary terminal voltage V2 is the phase difference of E2 and as well as what? Voltage drop. Voltage drop. You can observe here. This is the V2 and this V2 is equal to phasor sum of the inductive reactance and the resistance. Okay, what I am saying here, leakage reactance as well as what? Resistance. Here leakage reactance and resistance. This phasor sum of V2 is equal to the phasor sum of leakage reactance and the resistance drop, the subtract from the induced EMF E1. That is V2 is equal to E1 bar minus I2 R2 bar minus I2 X2 bar. So this is the phasor sum according to this step. The resistance and leakage reactance of the winding result in a voltage drop, and hence the secondary terminal voltage V2 is phase difference of E2 and the voltage drop. Voltage drop is what? I2 R2 minus I2 X2. So that's why you are getting here. Okay. So according to these 5 steps we drawn. Next step is step 2 draw. Next step is what? The resistance and leakage reactance of the winding result in a voltage drop, and hence the secondary terminal voltage V2 is the phase difference of E2 voltage drop that we already drawn here. That is V2 is equal to E2 minus voltage drops. Okay, and I2 R2 is in phase with the I2 and as well as what? I2 X2 is in quadrature with the I2. You can observe here. I2 R2 is always in phase with the I2 and I2 X2 is always quadrature with the I2. So according to that one only we drawn here. Okay. So next step is the total current flowing in the primary winding is the phasor sum of what? I1 dash and I0. Means I0 is what? No load current. I1 dash is what? Additional current of the transformer. So then you can observe the phasor diagram. Here the total primary current I1 is equal to vector sum of I1 dash and as well as what? I0. That only we drawn here. So next you can observe here the primary applied voltage V1 is the phasor sum of V1 dash and the voltage drop in the primary winding. So you can observe here the primary applied voltage V1 is the phasor sum of V1 dash and the voltage drop. What is the voltage drop here again? The resistance drop and as well as the reactance drop. Okay, so that is V1 is equal to V1 dash minus I1 R1 minus bar, that is I1 X1 bar. Okay, so according to this step. Okay, and next current I1 dash is the drawn equal and opposite to the current I2. Can observe here that current I1 dash is drawn equal and opposite to the I2 here. Okay, and next V1 is equal to V1 dash into voltage drop. We discussed that is, and I1 R1 is in phase with what? I1 and I1 X1 is in quadrature with the I1. Can observe here I1 R1 is always in phase with the I1 and I1 X1 is always quadrature with the I1. Okay, so next this is total phasor diagram of single phase transformer under inductive load condition. This is what? Under inductive load condition. So that's why the phasor difference between the V1 and I1 gives the power factor angle pi1 of the primary side of the transformer, and the power factor of the secondary side depends upon the type of the load connected to the transformer. So that is lagging for inductive load, for leading for capacitive load, for unity or in phase with that one, and getting the for resistive load. So this steps is common for inductive load as well as the what? Resistive load. Which is a changing here? Only the Power factor of the secondary side depends upon the type of load connected to the transformer. But remaining steps will be same for all types of the load. Okay. So this is the drawing of the phasor diagram for different types of the loads. Okay. So you can observe these diagrams. This is for phasor diagram of capacitive load. This is the phasor diagram of resistive load. Okay. So you can follow that steps only to draw this capacitive load as well as what? Resistive load. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.